In this lecture, we'll go through two of the slow variables constituting critical planetary boundaries that regulate under the hood of the Earth system, the big climate system, and the large operation of the global hydrological cycle and how biodiversity can operate in our living biosphere, namely land and water. And we'll start with land. Can you imagine, over just the last 150 years, we have rapidly moved into a situation where we've transformed almost 40% of the world's land area into urban regions and predominantly agriculture. And this enormous transition is illustrated through this series of maps showing the development over the last decades. Now, for land use, the absolute critical issue to recognize is that what determines the ability of land areas to regulate fresh water, regulate flows of different nutrients, be habitats for biodiversity, and regulate freshwater flows is what kind of ecosystems we have. And what we're finding is that the number one biome system to regulate the stability of the Earth system is our forest systems. And in the original planetary boundary analysis, we used a proxy to define and safeguard the critical forest areas in the world, namely what was the maximum amount of cropland that we could allow ourselves, because cropland is the largest human-caused land use change on Earth. And we used it because we have good data on cropland extent and cropland change. Now, in the updates that we're doing, we're focusing much more on what you see on this slide, namely directly analyzing how much of the different critical forest systems do we need to regulate the Holocene stability on planet Earth. And we're finding from science that the rainforests in the world, the temperate forest, and the boreal forest are the most critical ones in regulating Earth resilience. Now, we are so rapidly changing forest systems in the world. One very dramatic example is shown here from Borneo, where almost or a bit more than 50% of rainforests have been cut down so far in order to transform land use to large-scale palm oil plantations. And you see in this graph the transition of the growth of palm oil and the reduction in rainforest. And this has dramatic effects for local biodiversity, devastating effect for local indigenous communities, but it also directly affects the entire regulation of the climate system and the regional patterns of rainfall across vast areas. So these are truly regulating functions at the planetary scale. And we only have 3 remaining rainforest areas: the Indonesian, Southeast Asian, the Congo Basin in Africa, and the Amazon rainforest in Latin America. Now, the question one asks is, do these shifts associate themselves with tipping points? And evidence suggests that the answer to this question is yes. Very rarely or ever in isolation, but land use change can, together with changes in freshwater use, trigger large-scale, abrupt, and even irreversible shifts, what we call tipping points. When you change land use, we can have so large shift in freshwater flows that it could actually induce tipping points. Meaning, for example, when we cut down forests, take out fresh water in river basins, that we could have permanent tipping points where large tracts of land get locked into desertified states, as one example. So there are examples of how we can induce tipping points when pushing land and water systems too far. Now, nothing is static, and if you load climate change on top of this, we see projections into the future that will put even more strain on particularly freshwater systems. Here you see a very recent analysis by Jacob Shewe and colleagues at the Potsdam Institute for Climate Impact Research, trying to analyze what would happen with freshwater resources in the world at 2 degrees warming. So a point at which we most likely will be quite soon, already within this century. Now, if you look carefully at this map, you'll see the red areas in the world where the projections show, when we gather all the knowledge that we have today, regions that will lose 25 or more % of average annual runoff. And losing so large portion of freshwater resources is truly a risk of crossing tipping points where both ecosystems and food supply will be jeopardized. So these are examples of moving and the risks we would take if several boundaries move out of their safe operating space, in this case climate, land, and freshwater. So if you move into freshwater and the diagnostic of what makes water a planetary boundary, it's in its fundamental diagnostic the role water plays as the bloodstream of the biosphere. Water regulates everything we know in the biosphere. All vegetation growth, all biodiversity depends on fresh water. Humans depend on fresh water, and this map shows just the degree of water scarcity in the world as projected until 2025, taking into consideration freshwater needs in ecosystems and human needs. So what we're recognizing increasingly that the global hydrological cycle, which is finite, is fundamentally a prerequisite for the stability of the Earth system. It regulates climate, it regulates biodiversity, and it's also fundamentally important for social and economic development. Now, what makes water so interesting from a planetary boundary perspective is that it flows yearly in its hydrological cycle, evaporating from land and oceans, creating clouds, falling down as rainfall, infiltrating into the soil into what we call green water, the portion of rainfall that forms soil moisture and then flows back into the atmosphere as evaporation and transpiration, totally constituting vapor flows, and one portion flowing off on land and as groundwater flow, what we call blue water, the liquid water that fills up our lakes, rivers, wetlands, and dams. Now, what we're learning increasingly is that we have to have sustainable management of landscapes at large scale to safeguard rainfall, what we call precipitation sheds, which is what's the area that we depend upon as a source of our rainfall. And this is an illustration not only why water is a planetary boundary, because safeguarding the management of the freshwater cycle from the local watershed scale to the basin to the global scale regulates the entire flow of fresh water, which again regulates both climate and biomass, but also how intimately coupled freshwater is to land management and deforestation. So these are key justifications from science making water and land so important as planetary boundaries. Now the question is, how much water do we need to safeguard in order to stay in a Holocene-like state? In our original analysis, we did this from a global perspective. We looked at the global hydrological cycle. We looked at how much water can we take out in the large basins and biomes in the world before we start seeing evidence of tipping points, and calculated a global number of the maximum amount of water that we can consume in our rivers before we end up with a situation where we could see evidence of tipping points. But we did this from a very global analysis synthesized in literature. Now we're adding a very important piece to the evidence, namely digging ourselves much more down into detail in all the river basins in the world, exploring based on vast amounts of knowledge that is out in the field on how much water do we need to sustain in our rivers to keep ecosystems functioning, what professionals call environmental water flows. And what you see here in this graph is the latest update of a bottom-up estimate of the global freshwater boundary based on this analysis. For every basin in the world, what's the minimum amount of fresh water we need to sustain in order to keep basins resilient? And the exciting thing is that we're now combining these two analyses of a top-down global estimate of the planetary boundary for maximum amount of freshwater use with a bottom-up analysis of how much fresh water must stay in the basins to keep basins, large landscapes, operational. And this leads to our estimate of the final planetary boundary. But before coming to the numbers around where the boundaries land, let me just close with a kind of summary statement with regards to the importance of land and water for the human future on Earth. We are soon 9 billion people on our planet. Everyone with a right to development, and the basis for development will be access to food and fresh water. Recent estimates shows that just to feed humanity in a world in 2050 with 9 billion people will require potentially an increase of freshwater use from our current 7,000 cubic kilometers of freshwater per year, both in irrigation and rainfed agriculture, to in the order of 10,000 cubic kilometers per year. This in a planet where already 25% of our large rivers no longer reach the ocean because we're taking out so much water to produce food. Now the question is, can we transition the world on freshwater and land within a safe operating space. And John Foley and colleagues here at the Resilience Center recently did a very significant synthesis asking this question: can we feed the world within a safe operating space? And the answer is that yes. In fact, we have so many innovations and so much untapped potential to improve the efficiency and productivity of freshwater use that we can, in fact, attempt to achieve this grand challenge of feeding humanity within a safe operating space. Yes, we are in a very, very challenging position in terms of sustaining freshwater and land within a safe space. On the other hand, we can, within a safe space, also meet demands for a growing population. In terms of definitions of the boundaries then, what we've done is that the original estimate was to say, what's the maximum amount of cropland that we can expropriate, beyond which we risk tipping points induced by land use change. That estimate was set at a maximum cropland extent of 15%, and we have today transformed 12% of the world's land surface into cropland. It's 12% for cropland, but it's 40% if we include also grazing lands. But we took cropland because that's a set of data that we have quite a good handle on. In the updates that we're doing, we are, as I mentioned, reversing this to rather say how much forest do we need to maintain in order to sustain Earth resilience. And our estimate shows that we need to keep in the order of 75% on average for all the big forest systems. And we are today actually at a situation where we have cut down more than 25%. We actually only have 62% of forest left on Earth. So we're already in a danger zone with regard to the planetary boundary and forest. But importantly, we're actually able today to make the first estimates for how much rainforest we need to keep, and our estimate shows we need to keep 85% of rainforest systems, that we need to keep 50% of our temperate forests, which play a lesser important role in terms of its total coverage to maintain Earth resilience, and that we need to keep in the order of 85% of our boreal forest to stay within a safe operating space. And this is a signal or a way of showing that the planetary boundary at the global scale can actually be translated to the operational scale of forest management in large parts of the world. But it does, and I really want to remind ourselves of this, forests do not respect national borders. It shows that it's a global concern to safeguard the remaining forests on Earth. Similarly for freshwater, we maintain the original analysis that we need to keep consumptive freshwater use at the global scale below 4,000 cubic kilometers of freshwater per year. That is the boundary that we feel we still have evidence to support. But then we've done this bottom-up analysis of the amount of environmental water flow in all the basins in the world, which ends up with an aggregate boundary corresponding to in the order of the same magnitude as our estimates top-down. But it gives us percentages of maximum allowable withdrawable freshwater at each river basin in the world, which ends up in the order of 25 to 50% of fresh water must be kept in the rivers, and that there's a large variation here is that it depends for each basin on how much fresh water there is, if these are permanent basins, if these are intermediate basins, if these are only ephemeral basins, the flux intensity, etc. So there's a lot of intricacy here, but it just shows that we can operationalize this at the level of management. So overall, land and water as fundamental boundaries regulating Earth resilience and our desired Holocene state. They operate at the local level, but aggregate into impacts at the global scale, interact very closely with particular biodiversity and the climate system, and are fundamentally part of the operational management for a sustained, prosperous future on planet Earth.